In my experience, students usually after the second time through sequences and series, students feel like they actually understand them a little bit. But I've had students that go on to college and take Calc II a third time, and then they feel like they really understand them. All right, so a sequence. What do we mean when we're what do we just kind of everyday thinking? What are we talking about when we're talking about a sequence? Number. It could be numbers. Could be letters. They're in some kind of order, right? So sequence is some collection of objects in order. And the order depends on, what we mean by order depends on what kind of thing we're talking about. The definition that we're going to use, the one our book uses, is sequence is a function and defining it as a function is going to be useful in terms of the things that we do with sequences, whose domain is a set of positive integers. We sometimes include 0 as a domain value. So what we're saying is we have some f of 1, f of 2, f of 3, etc. So that's how we're going to think of sequences. We usually use subscript notation. So we would say A1, A2, A3, comma, dot, 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 to mean the same thing as this. And I'll say dot, 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 comma, A sub n. And I could do comma, F sub n. Because it could be a finite sequence. These are the terms of the sequence. And when we put it in braces, and I say A sub n, this refers to the entire sequence. So we list the terms individually. If we put it in braces, that's referring to all of the terms together. So we could say, just as a quick, easy example, we could say A sub n equals 2 to the n. So we would say A1 equals 2, A2 is 4, A3 is 8, comma, dot, dot, dot. And A sub n is 2 to the n. So our terms are, these are commas here. Two comma 4, 8 comma dot dot dot. We and when we have a formula for our term, we call this, we say the sequence is defined explicitly. So here we have an explicit definition of the sequence. We can plug in a number and find each term. Excuse me. We can also define sequences recursively. So a recursive definition is where terms, we define terms in terms of previous terms. We're using terms a lot of different ways there. So probably the most famous example of a recursive sequence, 1, 1, 2, 3, 5, 8, dot, dot, dot. Fibonacci sequence is a recursive sequence. Because for each term, to get each term, we have to add 2 previous terms. Now there is an explicit formula for the Fibonacci sequence, but it's kind of messy and complicated. And it involves the golden ratio. Golden ratio? 1 plus the square root of 5 over 3, divided by 3, something like that. And we'll talk. It comes up here and there when in the chapter as well. All right. So another example of a recursive sequence, we could say a sub 1 equals 3, and a sub k plus 1 is 2 times a sub k minus 1. So this is telling us the next term is the previous term minus 1 multiplied by 2. So we have a sub 1 is 3, a sub 2 is 2 times 3 minus 1, which is 4. A sub 3 is 2 times 4 minus 1, which is 6. A sub 4, 2 times 6 minus 1, which is 10, and we can go dot, dot, dot. So our sequence is 3, 4, 6, 10, dot, dot, dot. And sometimes it is possible to have a recursive definition for your sequence and come up with an explicit definition for your sequence. All right, we're good there. Okay, let me do this. I have some sequences and graphs. We want to match the graph to the sequence. 9. All right, so let's go through these. Number 9. So number 9 is 10. A sub n is 10 over n plus 1. I hear some C's. C. And so a couple of ways that we can think about this. So for number 9, what's the first term?
C.
5. So the first term we plug in n equals 1. C. You meant the speed of light, right? That's what you meant. It was a number. You said a number. So our first term is 5. That works out. And then as n gets larger, what happens to our terms? They get smaller, and the limit as n approaches infinity is going to go to 0. So that makes sense that it should be C. So 9 is C. How about 10? A. So our first term is 5 again, right? But that one gets larger, approaches 10. So we can think of the limit, right, as n approaches infinity. And we could use L'Hopital's rule on that. Or we could remember from all the way back from pre-calc our rules for horizontal asymptotes. The ratio of the leading coefficients, we think of that as a polynomial. So that would approach 10. So that one's A. How about 11? D just alternates, right, between positive 1 and negative 1. So that's going to be D. And then 12 has to be D. Whoops. This. That one's right. This one. They can be D twice. All right. So this one alternates between positive and negative, but the terms get smaller and smaller and smaller. All right. So a little visualization. What we're going to be interested in this chapter is the limit of sequences. We're interested in whether or not the sequence approaches the terms of the sequence approach some limiting value. And the limit of a sequence then is going to let us define the sum of a series when we start adding these terms together. So for the most part, we're interested in limits in this chapter. And interestingly, so sequences, they kind of can seem not really that interesting. You can define the real numbers in terms of sequences of rational numbers. So you can define all of our numbers in terms of sequences. And when you go further in math, when you talk about set theory, when sets are open, when sets are closed, all of that can be defined in terms of sequences and whether or not they converge. So sequences are an extremely powerful tool, even though we use sequences as a stepping stone to get to series. They are a very powerful tool. So what we're interested in now is the limit of a sequence. So let's talk about our definition of the limit of a sequence. So I'm going to say L is a real number. The limit of a sequence is L, or the way we often write it is the limit as n approaches infinity of a sub n equals L if, I love this part, for each epsilon greater than 0, Oops, epsilon. For each epsilon greater than 0, and I like to include no matter how small, for each epsilon greater than 0, there exists m greater than 0, so that the absolute value of a sub n minus L is less than epsilon if n is greater than m. Well, that wasn't bad. Usually when I mention epsilon, there's lots of moans. So there are just a few this time. And it's better because our definition of a limit of a sequence doesn't involve a delta. Instead of delta, we just have m. If this limit exists, we say the sequence converges. Otherwise, we say it diverges. And I'll draw a picture here in just a second, but I just want to talk about what this definition tells us. This definition tells us that eventually, when n gets really large, the distance between each term and the limit gets really, really small, because epsilon can be as small as we want. That's what the definition tells us. So this epsilon definition is lets us explicitly and rigorously define what we mean by close to. We say it can get as close as we want, because we can make epsilon as small as we want. So it's the distance between our term, nth term, and the limit gets as small as we want. So graphically, what this says. So I'm going to draw a little graph and we'll plot our terms. And this is just some arbitrary sequence. So I'm going to say this is L. And we said back here, let me go back, the absolute value of a sub n minus L, that's the distance between our nth term and the limit. So what that means is we have L plus epsilon here and L minus epsilon here. And this is going to give us this band in here. And I'll do my L in red. And we're going to do our first term, second term, third term, and dot, 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 dot. And out here we have some m. So it says, say the first term is here. And the second term is here. And the third term is here. And the fourth term is somewhere else. What it's telling us is eventually my terms are all going to be inside this band. So eventually, no matter how small we make epsilon, all the terms are going to be right there really, really close to L. That's what it's telling us. We can pick an m large enough to guarantee that happens, no matter how small epsilon is. So depending on your sequence, m might have to be really big, but if your sequence approaches a limit, we can find that m that guarantees that all of the terms are going to be really close in that tiny little band of values around L. So that's what that definition is telling us if we look at a picture. Eventually, all of our terms are going to be inside that band. Now, the nice thing about limits of a sequence, and based on how we define them, we define sequences as functions of the positive integers. We can use everything we know about limits of functions to work on limits of sequences. So that's exactly what we're going to do, is we're going to take advantage of that definition of the terms of our sequence being a function. So I'm going to say let f be a function. So that the limit as x approaches infinity is L. I'm going to say if we have this sequence a sub n where f sub n equals a sub n, or f of n equals a sub n, so for our positive integers, the terms of the sequence equal the function value, then we can say the limit as n approaches infinity of a sub n equals L. So we just associate the terms of our sequence with a function, the function that explicitly defines our terms of our sequence, and then we can use everything we know about limits of functions to discuss or to find the limits of sequences. So all the things we know about limits of functions we're going to apply to sequences. All right, we good there? So let me remind you of some properties of limits, because they're going to be, they'll be helpful as we work, or they can be helpful as we work on limits. So I'm going to say the limit as n approaches infinity of a sub n equals L, and the limit as n approaches infinity of b sub n equals k. So we have these two sequences. We can add limits together, add or subtract. A sub n plus or minus b sub n is L plus or minus k. And I'm going to say C is a real number. The limit as n approaches infinity of C times each term, we can factor out that C. C times L. We can multiply and we can divide. As long as b sub n not equal to 0 and k not equal to 0. So sometimes it's helpful to break apart a more complicated sequence into a sum or a difference or a product or a quotient and look at each piece separately. All right, questions? Our homework tonight, I think, is just looking at sequences, maybe recognizing some patterns, and maybe finding some limits. All right, there we go.